So this is the introduction to forces, and we can split forces into two main types: contact forces, as the name suggests, direct contact is made in the interaction, and non-contact forces, which are forces that can act at a distance.
For a contact force, we might want to look at a distortion, and almost every object that's in contact with another force is distorted. So I could distort my nose, for example, and we could see clearly there is a contact force between my finger and the nose. Similarly, if I were to get a sponge, I could actually look at the sponge and we could compress the sponge. We can see very clearly the distortion in the sponge. But if I keep a piece of metal and push the piece of metal into the sponge, we can see the sponge has got a distortion, part of the contact force. But the question is, does the metal have a similar distortion? And what if I were to get two metal pieces and push them together? We can't see any distortion here, but has a distortion happened? And the answer is yes, there is. If we were to look at it from an atomic level, we would see that the layers of atoms have actually been squashed together in quite a similar way to the way the sponge has. So one of the contact forces is friction, and it's often misunderstood because some people feel that friction is only about solid bodies. So if I rub my hands together, we can feel the force of friction, slowing it down. It's acting in opposition to the motion. And the work done is actually causing a heating effect. That's why if you want to make your hands warmer, you can rub them together. Friction is sometimes useful to us, and sometimes we actually don't want friction. So if I take a skateboard for an example, on the top of a skateboard I have grip tape, and this is sandpapery type stuff. It's very high friction, which prevents my feet from slipping off it. Hence I really need the friction on there. If you try and ever ride a board without the friction, you'll find your feet just slip off. When we come to the bearings, we want our friction in the bearings to be as low as possible as well. We want the wheels to run as freely as possible, and so often we lubricate the bearings in order to reduce that friction forces. The wheels themselves, we've got a couple of completing factors here. So when I want to go in a straight line, I want friction to be as low as possible. It's much easier to skate on a smooth surface than it is on a rougher surface. When I come to a bend, I actually don't want my friction to be low. I want my friction on my wheels to be as high as possible. And the reason for that is, remember, that forces cause a change in motion. If the force isn't great enough, there will not be a change in motion, and hence I will carry straight on. I will not go around the bend. And the steeper the bend is, the greater the friction I'm going to need. And that becomes down to the fact that when I'm changing direction very quickly, my velocity is changing. If my velocity is changing, then I have an acceleration. I have a change in motion. Whenever I have a change in motion, I need a force to do that change in motion. So the steeper the bend is, the greater the change in velocity, the greater the acceleration, and the greater the force needed. So another contact force is buoyancy. Buoyancy is directly in contact. We normally associate it with liquids. And what happens is, if I were to put a table tennis ball into a glass, we can see that what happens is the table tennis ball floats. It's got an upthrust, sometimes called. And what's happening is that the force going downwards, the weight of the table tennis ball, is being exactly balanced by the upthrust produced by the liquid. We know that the forces are balanced because there's no change in motion. It's in a stable state. If I were to take something which has a greater density than water and we put into the water, we can actually see that it sinks. And the reason why it sinks is that the upthrust force is not great enough to balance the force of gravity, and hence the body sinks. Gravity is one of the non-contact forces, and we're very aware of gravity because we can feel it. If we fall over and we hit the ground, and we hit the ground because of the force of gravity. If I were to lift a mass up, we can feel its weight. We can feel the gravity, the force of gravity pulling it down. However, gravity is not just to do with the Earth or big bodies like the Moon or the Sun. Every object exerts a gravitational attraction on every other object. So you at the moment are exerting a gravitational attraction on the person next to you, and they're exerting a gravitational attraction back. You can't feel it. And the reason you can't feel it is because it's very, very small. It depends on the actual size of the mass. So the greater the mass is, the greater the gravitational attraction. So here I have a mass of 1 kilogram and here I have a mass of 2 kilograms. We can't feel it, but what should be happening is the force going to the 2 kilogram is actually greater than the force going to the 1 kilogram. So if those forces were bigger, what would actually happen is my head would be moved towards the 2 kilogram mass and not towards the 1 kilogram. The other thing people tend to think about in gravity is that, that the Earth exerts a force of gravity on the Moon, but the Moon doesn't exert the same force of gravity back. It does. Every time there's a force, there's an equal and opposite force in the other direction. So if I were to jump in the air, so I was off the Earth's surface, would the Earth follow me? Have I exerted a force on the Earth? And the answer is yes, I have. There would be a tiny, tiny, tiny bit of movement from the Earth following me because I would be exerting a force on the Earth, and every time we exert a force, it creates a change of motion if that force is unbalanced. We can use a balloon and we can use a doll and some wool. So the first thing I'm going to do is an everyday description. So the first thing is I rub the balloon against the wool, and then when I move it close to the hair, what we can see is that the hair moves even though there's no contact between the balloon and the hair. So magnetism can be considered to be a non-contact force, because if I take this magnet, I can actually create a change in motion without there being direct contact between the magnet and the object. Hence, it's a non-contact force. The nuclear force doesn't really come into GCSE, so it's not something we need to consider too much. But some of you might have considered at some point the fact that when we look at electrostatics, that inside the atom we have a whole load of protons in the atom with the electrons whizzing around the outside. Now, the thing about like charges is like charges repel, so the question really ought to be, with all of these protons in the middle of a nucleus all close together, why doesn't the atom blow apart? And the reason for that is the nuclear forces, which are actually within the nucleus, as the name suggests, of the atom, which is preventing those atoms from blowing apart.